Great. Thanks to the organizers and for this wonderful meeting. It's great to see everybody. Thanks to Juan for introducing our subject so beautifully. So I'm going to summarize cosmology at the theory frontier based on a white paper that we're writing for both TF01, this session, and TF09, the Astro and Cosmology session, in progress with these wonderful younger authors. And as Juan already so beautifully described, this subject spans real observations, really serious observations, confirming a very simple model of the origin of structure in the universe. Ranges from that to thought experimental questions such as the microstates of space-time and related questions. So it's a wonderful subject, too big to really cover in 20 minutes, but I'll do my best to sample from this subject, focusing on recent developments and big questions. Okay, so just to get us on the same page, it's been 20 years since we understood that the universe is accelerating in its expansion. There's also loads of evidence for that having happened in the early universe inflation, where the expansion of the universe is accelerating as a result of a slowly varying source of energy, most simply modeled as a slowly varying potential energy for a scalar field, say. And from that general idea, which solves the macroscopic problems, we'll come back to that question of how it solves those shortly. You have also a big payoff, which is that field, that scalar field that was introduced to get the inflationary effect to end, the strong early universe accelerated expansion to end, that scalar field has irreducible quantum fluctuations, which freeze out outside the Hubble scale during the process and lead to seeds for structure in a way that is the essence of quantum mechanics, the variance or the uncertainty in the field fluctuations delta phi. Okay, so we measure the effects of this through various observations, so far mostly through the CMB, which streams to us from when atoms first formed and carries an imprint of density fluctuations that arose much, much earlier. Recently, we can continue with CMB in a big way, but also there's a major push, and that includes both observation and theory coupled together, to extract as much information as we can from the large-scale structure of the universe, which is more nonlinear, but has more modes, more independent experiments in essence. And so there's a great theory problem to not only interpret and predict signals for this, but also to extract the information from it, which brings in also beautiful ideas of theory like effective field theory and other methods. Okay, so we heard already that quantum mechanics accounts for the seeds of all structure in the universe, that this is a relative of the black hole Hawking radiation. I might have said it goes the other way, that cosmology informs the black hole case, but never mind. So in cosmology, there was an early set of calculations of inflation's predictions for those fluctuations in terms of calculations of the variance of the field in the early universe. This was translated by Bond and Eustaquio in classic work to a prediction for what we actually see in via the CMB. And that prediction, the structure of it, was beautifully demonstrated by the resulting CMB series of CMB observations. Most recently, Planck, where I've plotted here the 2-point function of the temperature variations. Oops, going backwards. Okay, so that theory of the origin of structure is a beautiful and successful and really quite a deep theory as an effective theory. But as we all know, it requires what I would say both a UV and an IR completion. Things kind of break down on us in both ends of that spectrum. So here I've kind of given a cartoon of the problem we face. So there's a patch of the universe that we see from which we infer various aspects of the primordial probability distribution for the fluctuations in the early universe via the CMB and large-scale structure, as we also map out the cosmological parameters, giving the macroscopic evolution of the system. So that's a beautiful story that I just very briefly summarized. And it connects to the theme of this session, quantum gravity, in a beautiful and as way that's as direct as it gets in connecting quantum gravity to observations. In that, from a Wilsonian point of view, every model of early universe inflation is UV sensitive. And so from that point of view, from a theoretically responsible point of view, a satisfactory theory of it really requires an understanding of those effects, even though it's the case that we describe and classify these perturbations perfectly well from the bottom up. And we already see some testable signatures from string theory versions of inflation. That includes B modes, features in the power spectrum, and non-Gaussianity. But there is clearly a bigger picture here. So if we look at horizons in cosmology, there's old work from the 70s, similar but a little less clear than the work on black hole thermodynamics, but also suggesting that the horizon in cosmology might carry with it a prediction for a number of states associated with these horizons that would be the exponential of its area over 4 in units of the Planck scale. So that gets us into a thought experimental piece of data that we want to also understand and explain. From the top-down string theory point of view, at least, and maybe other considerations, we have lots of reasons to believe that the accelerated expansion doesn't persist indefinitely into the future. That's why I've drawn these little diamonds relating to predicted decays at exponentially long times. So if you like, that's infrared, also connected to the UV physics of such decays in string theory. And, you know, as long as we're on the subject, we have to account for the possibility that globally there are different components of the universe, different topologies. And as was already said in Juan's talk, singularities need to be understood. Okay, so this is a big combined challenge, grounded very beautifully on real observations, but taking us much further. Okay, so there have been, despite the challenge, there have been really remarkable recent advances and lots of opportunities in this direction. Okay, so just a quick outline of our paper in progress with a smattering of highlights that I'll cover as much as I can of today. Oops, I keep going backwards. Okay, so these primordial perturbations organize into a scalar mode and a tensor set of tensor modes in the primordial bottom-up theory. So there's some wave functional of those modes, along with whatever additional fields might have been around. We can translate that into a probability or a likelihood by squaring that wave function. And what we're really doing is asking how likely the data is according to a given theory of such a likelihood. And so far, a very simple Gaussian theory with small tensor modes fits the facts. But this is the bigger picture. Even at the level of the 2-point function or the variance, we have a function's worth of data, the power spectrum. Okay. Now, theory is really heavily involved in this. This is already clear from the historical example I gave. And when it comes to the UV sensitivity, this is a standard thing, but it bears saying that any model of inflation, if you add to it so much as a Planck suppressed dimension 6 operator, the slow roll parameters in, say, a slow roll inflation case change by order 1, whereas they need to be a percent level. So we're highly motivated and have been for 20 years now to pursue the study of this process in string theory. And there we find that while a generic sort of effective field theory notion would say that even at tree level, you could have arbitrary contributions infecting the potential at scales in field range of order a Planck scale or less. In certain directions in field space, like axion directions, we find a much more regular structure. And there are many, many, that's just one of many, well, of a good collection, not many, but a good collection of inflationary scenarios in string theory that fall into broadly distinct classes that are distinguishable, in some cases falsifiable, by early universe observations. It's important to state that these are model dependent. There's no responsible way to give an overall overarching prediction for the various observables from string theory as we understand it. But this model-dependent discrimination is interesting enough. And the data here, I plotted the tilt and tensor to scalar ratio, the way the power spectrum varies with scale, and the amplitude of these primordial gravitational waves that have been mentioned, and how the experiments have progressed, most recently here with the bicep Keck latest. And in the context of a top-down theory like string theory, there are degrees of freedom that tend to adjust, kind of flattening the potential, and multiple field effects can also be understood to push on the tilt in a certain way. And it is very exciting that these measurements combined with these theoretical lessons can teach us a lot about what was or was not going on in the early universe. Okay. So as I said earlier, there's a big and probably impossible job of really classifying the possible ways that this initial probability distribution could work. There are many ways to be non-Gaussian. We can, to some extent, put those into different categories, like effects of additional fields, single field self-interactions that slow the field on the potential and thereby generate, even at the single field level, large non-Gaussianities. Various things coming from axions that involve oscillations and other such effects. But this is hardly a systematic study of this gigantic functional in the early universe. Let me highlight a few recent advances in these directions. And this falls into roughly two categories. One is sort of perturbative structure, sometimes all order statements, and non-perturbative structures. So we already heard a bit about bootstrappy ideas here and amplitude ideas. And what this side of the board usually does is assume a high degree of symmetry and then come to prove very interesting theorems given that assumption. So in that sense, it's kind of conservative observationally. It zeroes out couplings that could be there in inflation, but as such is maybe less conservative theoretically. If you allow anything that can happen consistently with our knowledge of inflation to happen, then there's a wide range of phenomena that can even be, to some extent, calculated non-perturbatively that assess, for example, how heavy the non-Gaussian tail is in this early universe set of perturbations. And there's a growing set of works, and Bond and company have been doing this for years, spelling that out in different cases. Hyperbolic field space arises in various contexts of supergravity and string theory, leading to a super heavy tail. And in this case, there's a grand challenge to understand how to characterize these in a way that can be tested most usefully. These are two directions in that vein. Continuing with the bottom up, another highlight is recent results that show just how robust inflation is, given even very wild initial perturbations. One can pursue numerics and also do some proofs of theorems in combination with mathematicians that prove that with even large deviations from, say, the Bunch-Davies vacuum, inflation nonetheless sets in. Eventually, there's this question of space-time singularities. We see in the context of string theory how at various singularities some stringy effect enters, but that's far from a complete theory of this question. And there's not much news there, so I'll leave it at that on that question. So the wave function of the perturbations can be really quite varied and still consistent with inflation and observations. What about the wave function of the universe itself? That's a wonderful question. The executive summary is we really don't know, but there's been a lot of discussion and debate about it over the years. One interesting possibility is the so-called Hurdle-Hawking or no boundary proposal, where you assume, say, in some Euclidean quantum gravity instanton-like calculation, that the saddle point solution is smooth geometrically before it continues to Lorentzian evolution. And there's one highlight of recent works which shows that if you make that assumption, you really do have to include multiple topologies. And if you don't, you would have gotten an inconsistent state of matter in the wave function produced by this path integral thus defined by the no boundary proposal. So that's a very intriguing result. It was done in the context of ADS-CFT, and it remains to be understood exactly how that plays out in cosmology, but it's a great question. Now, regarding choice of state, we have toy models for quantum gravity, like the good old string worldsheet itself, which clearly have multiple states available. And there's some beautiful work culminating in some papers by Martinek that show how cosmological evolution can appear on the worldsheet. And so how the choice of state appears is interesting to consider in that much more understandable context. There's another development that involves multiple states that I'll get to shortly. So these are great questions. It's difficult to really come to a conclusion about them, so we work more step by step. And let's go back to this prediction, or sort of prediction, of Gibbons and Hawking, with corrections recently computed, in fact, by the Aninos et al. Group, suggesting that the horizon in cosmology, the area of the horizon, predicts a certain number of microstates. Now, this is an ongoing effort to try and understand the upgrade of ADS-CFT to cosmology. There are a lot of ideas and approaches in various stages of development. I will take the liberty of showing you my favorite of these, which is, I can summarize as follows. So if you take, you go back to the black hole version of this sort of question, where you have a prediction there of the area counting microstates, there's a classic calculation in the field due to Strominger and Vafa, which obtained that predicted result by starting from a weakly coupled description and moving using the power of extended supersymmetry to control the space of states, the count of states along such an interpolation, giving a successful count for certain black holes in string theory with this quite enhanced amount of supersymmetry. What's happened recently is, due to efforts of Zalmalajikov et al., Dubosky et al., Kavli et al., and so on, there's another type of control deformation that has nothing to do with supersymmetry that has been understood. And in that case, one can deform a theory, keep track of its energy, spectrum, and count of states, even if the theory that one starts with in doing such a deformation is not integrable itself. The deformation is integrable, meaning you can keep track of these energy levels. And there's such a theory that starts from a CFT, deforms it in a way that uses and generalizes the solvable integrable deformations that I just kind of summarized in such a way that the energy spectrum and the count of states match the geometry and the predicted entropy of the de Sitter observer patch. So if anyone would like to discuss that more, I'd be very glad to. But the general slogan is new type of controlled deformation and a theory that matches the geometry and the count of states of de Sitter in low dimensions. Okay, so in the middle between these perturbative and observational results and the grandest questions of wave functions of the universe, measure, and so on, lies string theory and cosmology, where we work out the structure of de Sitter and inflation in string theory in quite a bit of detail. So this leads to those model-dependent UV-sensitive tests that I mentioned. It's related also to these questions about the microphysics of de Sitter quantum gravity. And recently, there's been even a bit of a connection to industry, if you like. Okay, so I need to go through this quickly. There's a beautiful semi-recent work by Douglas that's quite model independent, laying out the effective potential that we get from any extra dimensional theory, such as string theory. What enters into it is the dynamics of the warp factor, properly solving the constraints of general relativity, which enters importantly, and the various stress energy sources and the curvature, the effect of the curvature of the internal dimensions. So we have a pretty systematic understanding of these things, and there are various contributions that arise depending on the type of compactification one considers, curved or not, and quantum effects, or at least effects beyond general relativity, enter in also in an important way. So I highly recommend this paper if you want a general picture of how these things go. There are now an assortment of interesting models that hang together. They roughly classify into power law stabilization, going back to examples based on the very leading term in the effective potential, which is positive, and non-perturbative stabilization. They hang together with various control parameters. And I don't have time to go into details, lucky for you, because the details are detailed. Okay, one thing to stress is the universality of axions in string theory. If anything's universal, as far as I can see, it's that. Other model-dependent quantities like low or high energy supersymmetry and even large radius gravity are quite more model-dependent. The way axions work in string theory and the way they couple to fluxes is very interesting and important in early universe physics. And in fact, there's a time-dependent large field range that has an effect on other degrees of freedom, but in explicit models, this is found to be a small effect over the 10 Planck units of field range required. And you can delve into the literature to see that, and it remains a very interesting and important direction, as Juan stressed. Okay, in the case of Clavial compactification, the news is very explicit realizations of the control parameter involved in those, and also beautiful studies of the statistics of axions in those models. There typically are many axions, and one finds that whereas quantum gravity could have ruined the Paget-Quinn symmetry and the strong CP solution in certain calculable corners, this is work of McAllister's group, they found that things work out very, very nicely to have explicit formulas. Another recent advance is parametric control parameters in hyperbolic internal dimensions, which are generic when it comes to curved internal spaces. They have a rigidity property that's particularly important. With observables, we have Gaussian observables, which are making a great deal of progress. I already gave some interpretation there. Structure in the power spectrum can be imprinted by quantum gravity and other field theory models. In the CMB and large scale structure, there's a grand challenge to extract the information that we know should be there. And let me just say, it's a non-perturbative challenge in all senses. So we want to understand these heavy tails and from the quantum field theory point of view. And to get them out of LSS, maybe kind of non-perturbative in that EFT. And so it's not only a generic question, but it's an interesting one theoretically. There are connections to mathematics, compactification geometry, and industry in the sense of machine learning playing a role, both to help calculate features of the internal dimensions. And recently, cosmological evolution has inspired a new algorithm for machine learning optimization. Okay, so I should conclude. And so let me do that and leave you with these conclusions. Thank you.
Thank you, Eva, for this tour de force. Are there questions for Eva from the...
Maybe a naive question from an outsider, but in this program, do you have a way of testing the reheat temperature in a perhaps way that's independent of the inflation model? Like perhaps there's some observable?
So, sorry, can you say that again? I just
yeah. Do you have a way in this program of testing the reheating temperature?
Oh, the reheat, right.
Yeah.
I thought you said reaching temperature. And I was
No.
like, okay, sorry, the maths are fine, but that is a wonderful question. I meant to mention that. There's been a lot of interesting work on just specific, to be specific on oscillons. And there was even a whole program here trying to see what might come out of what basically look like those dark ages of reheating. Can you get a gravitational wave signature from particularly violent events during that period? It's a great question. I don't think there's a firm no-go on that, but it is difficult. But yeah, the short answer is it's on the agenda. There's interesting calculations of effects that can be have interesting properties like long-lived oscillon modes in the field, and but getting that to transmit to us a signal is not trivial. So reheating can work in so many different ways. And
are there comments or questions in Zoom land?
So I don't see. Oh, we got a hand up. Oh, from John Martrussell. John, go ahead and unmute yourself and ask your question.
Hello. Thank you, Eva, for a very nice talk. You touched on this very quickly. There's a lot of very nice work on thinking about the initial conditions for inflation and showing more general conditions work. But nevertheless, as we push down R, that initial state becomes more and more surprising. What is your personal view about what we might be learning? Imagine R really gets down to 10 to the minus 4 or something in future decades.
Yeah, no, that's a great question. So we are in the middle of determining whether inflation is large or small field. And what John is asking is, suppose it ends up being small field, your basic question was, how do we interpret that? And also, particularly, how do we interpret that in the context of the initial conditions, the robustness of inflation? There is a standard landscapey answer to that, which is that if what we see was prior to what we see was a bubble decay from one of these vacua to another, you start then with a homogeneous negatively curved, now I'm talking about the 3 + 1 dimensions, negatively curved 3-dimensional slice that evolves forward and just starts its life homogeneously. So the patch problem in that sense may be okay, even in small field inflation. That's that's a certain point of view that's been proposed. That's the only answer to that question that I'm aware of. Yeah, there, of course, it's at some level it's tied up with measure questions as well, which are very hard to evaluate. But from a very, very naive point of view, you might say when inflation succeeds, it takes over anyway, and so on. But yeah, I tend to agree with you that everybody knows the patch problem is less severe in high scale inflation.
Yes. And
the observations remain to discriminate, but the prognosis for that is really very, very good. I mean, it's remarkable that it's made the progress it has, and it's already starting to make statements. For example, there's a new parameter beyond m squared phi squared inflation for sure. And so I'm confident as much as one can be that the observations will get there, and then we can interpret.
Mm-hmm. Can I also make a comment? Am I allowed to make one comment, possibly, for
Please.
task force? So, there are other things, of course, directly connected to inflation. So one of the very interesting things, there's this beautiful mechanism done by Peter Graham and Jeremy Marden and Sajid on dark matter production, inflationary mechanism. So that produces a spectrum which has a huge amount of large-scale structure. Small-scale structure, and possibly observable. So it could be that we have other very direct probes of inflationary dynamics. And I think that there's an interconnected story there that would be quite interesting to talk about.
Great, that sounded interesting. I didn't hear all of it, but I'd like to. Yeah, maybe.
Okay.
I mean, I can.
Let's move on to the next question, if I may. Was that a raised hand? Did you?
It was kind of discussed.
Okay. Are there other? Oh, hold on.
Yes. So can you elaborate? What do you think you can get from the TT bar program, please?
Well, I would love to, but I can't. I don't have time, probably. Yeah. So what's striking to me is that both the geometry and the count of states arise in a genuinely calculable way from a solvable deformation of a CFT, starting from the black hole result of microstates. Those dominate the spectrum that gets deformed. The real part of the spectrum. So there's been this old idea that the pseudo prediction by Gibbons and Hawking of a horizon entropy would be captured by some theory with a finite Hilbert space or finite part of a larger theory's Hilbert space. In these deformed theories, the real spectrum is finite. In TT bar deformations, as you may know, the formula for the deformation of the energy levels has a property that above a certain seed energy, they go complex. So if you prioritize unitarity and you just take the real part of the spectrum, the count of states of that matches precisely with what is predicted for the horizon. That at the same time that the defined deformation here that I'm alluding to reproduces also the geometry of the sitter via the fact that the same energy formula, whose state count we can follow, the energy formula itself matches Brown-York energies in that patch of space-time. So it's a very concrete statement. This theory, I should say, captures those things and nothing else. It does not capture the details of local bulk physics that should come with additional currents in the deformation. So bulk physics, light fields will be, naturally light fields will be gauge fields or axions or things like that that require adding other currents beyond the stress energy tensor to capture. But these leading questions about the geometry and the entropics are captured by this theory in a calculable way. So how to go further? One wants to see if one can define it in higher dimensions, if one can add the bells and whistles for the local bulk matter in any dimension. And there's a lot of ongoing research on that. So I take this result as most conservatively as a humongous motivation to really do that, to really make sense of TT bar in all its forms. So is that what you're asking, basically? Yeah, I'd be very happy to talk more.
Thank you. We are at the end of the time for your talk. Eva, thank you very much. Eva?